Thanks, Yuko, for the nice introduction. And good afternoon, everybody. I'm Masashi Sugiyama. Sorry that I'm joining from Tokyo today. And actually, Tokyo was quite chilly in the morning today, and we had even snow. So I hope everybody is enjoying good weather in Okinawa. I really envy you. So my lecture today is about machine learning from weak supervision and empirical risk minimization approach. So here's a QR code. So if you want to see a slide, so you can just take it. If you have a nice smartphone, you may magnify this and take it. Or I pasted the URL in my Slack channel. So please look at it. Okay. So then what is this lecture about? So we are sure that machine learning from big label data has been very successful in many applications like speech, image, language, recommendation, etc. However, there are still many applications where massive label data is not available. Like in our Riken Center, we have project on medical sciences, natural disasters, robot control, brain signal analysis, etc. So in these applications, it's very difficult to obtain high quality label data, or sometimes even impossible. For example, in the case of natural disasters. So we have a lot of typhoons in Okinawa, but still we can't call it big data. Still the amount of data is limited. So this is the target problem today. But this is not really a special problem. So we are aware of this issue for a long time. And there are many approaches to coping with high label cost problem. Maybe a natural thing is to improve the data collection process. For example, by using crowdsourcing. So we ask crowd workers on the web and we obtain reasonable labels with low cost. But often this approach provides really noisy labels, and handling noise is a big issue here. Then another approach is to use a simulator to generate pseudo data. So this is often possible in like physics problems like earthquakes analysis, or maybe driving simulators can also be used. But such a simulator is not always available. And a typical standard approach is to use domain knowledge. That means we engineer hyperparameters or neural network architecture, etc. So such an effort is anyway needed in all applications. So we, of course, use it. Then finally, so this is the target of this lecture, we try to use cheap but weak data. Ideally, we want to have clean, high quality label data, but sometimes it's not easy to obtain such good labels. But depending on some applications, we can obtain some weak information easily. I will talk about it later in detail, but unlabeled data is, of course, a natural example of such weak data. And we want to have high quality classifier in the end, only from weak supervision. So that's the target of this lecture. And here is my disclaimer. So this learning from weak supervision is really a hot topic, and we can find a lot of great papers in conferences and journals. So therefore, the coverage of this lecture is extremely biased and limited. So this is something we can't avoid. So please take that into account. Okay, so for the moment, let's consider the simplest problem, binary supervised classification. So we are given positive points and negative points, and we want to learn a boundary between two classes. So this is a standard binary classification problem. And we know that a large amount of label data yields better classification accuracy. And under some standard setting, we know that the estimation error of the boundary decreases in the order of 1 over square root of n, where n is the number of label samples. So 1 over square root of n is a function like this. So this means if we want to halve the estimation error of the boundary, we need to collect 4 times more samples. So that's the kind of general phenomenon. And we can somehow justify the use of big data by this standard theoretical analysis. But as I said, so increasing n number of label samples is sometimes very expensive, or sometimes even impossible. So that's the challenge here. Then one extreme direction is to use unsupervised classification. So here we don't use labels at all. So let's use unlabeled data only. So black points are unlabeled data in this case. And here's a classical example of 2 moons. But unsupervised classification is basically clustering, unsupervised clustering. So there's no supervision. So what we can do the best maybe to split unlabeled data into separate clusters like this. Then if you are lucky and one cluster corresponds to one class, then such a clustering-based approach works quite well. But in practice, maybe often the case in practice, so one cluster may contain samples from different classes, so they are mixed. So such a clustering-based method does not work well. There's no guarantee that the solution is reliable. Then the popular approach is semi-supervised classification. So in semi-supervised classification, we use a large number of unlabeled samples and a small number of labeled samples. So if we continue using the same 2 moon example, so in addition to a large number of black points, so we have one blue positive point here and one red negative point here. So this is a typical textbook example of semi-supervised classification. But again, so in this semi-supervised classification approach, classically, so the methods try to find a boundary along the cluster structure. So this basically means some kind of clustering is involved in the semi-supervised learning process in many cases. Then we end up in having this kind of boundary between 2 classes. But now we have additional labels, blue and red. So this blue color may be propagated across over this cluster, and this red point may be propagated along this cluster. So then we can somehow color each cluster separately. But again, if one cluster corresponds to one class, such an approach works quite well. But in practice, maybe one cluster is a mixture of several different classes. Then this kind of label propagation idea does not work well. So then summary so far. So I took the labeling cost on the vertical axis, low and high. Then classification accuracy on the horizontal axis, low and high. Then supervised learning has used all labels. So then its labeling cost is the highest, so on the top of the figure. And the classification accuracy is high enough, because if you have clean label data, then supervised learning is the right method to use. So this is located on the top right corner of the figure. Then unsupervised learning, so it doesn't contain any labels. So then the labeling cost is basically 0, so it's the lowest. But the classification accuracy is not really reliable, so it depends on maybe cluster structures. Then, so unsupervised learning is located on the bottom left corner of this figure. Then the last one, semi-supervised classification. So this is slightly higher, the labeling cost is slightly higher than unsupervised learning and much lower than supervised learning. So it is located somewhere here. But again, the classification accuracy is not necessarily reliable. So it is still located on the left half of the figure. So our target today is this bottom right corner of the figure. So high accuracy and low labeling cost. We want to have a classification method that achieves this goal. So this is the target of this lecture today. Then here's the textbook. So thanks to our former student and colleagues, so Hanbao, Takashi Ishida, Nandu, Tomoya Sakai, and Gan-New, we published a textbook on machine learning from weak supervision and empirical risk minimization approach. So this is exactly the title of this lecture today. So it has 320 pages. So it's a thick book, but it contains all about basics of machine learning from weak supervision. Again, this is quite biased because it's a book. It's a book contains like our views, but I hope this gives a kind of nice basis of machine learning from weak supervision for many researchers and also practical engineers. If you have a chance to take a look at this textbook, please take a look at it. Okay, so then for now, so in the next 5 minutes or so, let me quickly introduce some typical weakly supervised learning problems that I want to discuss today. And the first problem is called PU classification. So P is positive and U is unlabeled. So it's positive unlabeled classification. So we are only given blue positive points and black unlabeled samples. So unlabeled samples are basically a mixture of positives and negatives. And from PU data, we want to learn a decision boundary between positives and negatives. So we suppose we have negative points, red points on the right-hand side, but they are completely missing. So a textbook example of this PU classification is click prediction in advertisement. So suppose certain advertisement appear on the screen and a user clicks it. Then such an advertisement is collected as a positive sample because the user may be interested in that advertisement. But suppose there's another advertisement that appeared on the screen, but it was not clicked. Then intuitively, so we want to collect such unclicked, non-clicked advertisement as negative samples, but this is actually not always true. The advertisement appeared on the screen and user didn't click it. Maybe because he or she is not interested in that advertisement, or he or she was interested in that advertisement, but they didn't have time to click it at that moment, or maybe clicked another advertisement or something like that. So then, in principle, so unclicked advertisement should be treated as unlabeled data because they can be either positives or negatives. So this is a natural example of PU classification. And the similar situation also happens in like friend, non-friend prediction. The non-friends are usually not recognized, so clearly declared. So then, such relations should be regarded as unlabeled data. So in that situation, we only have blue points and black points, but still we want to separate blue and red. So this is PU classification. And we can show that this PU classification can be really solved in a nice way. So this is one of the main topics today. Then the second problem is called P-conf classification. P-conf is a short form of positive confidence. So ideally, we want to extend this PU classification to P-only classification. But only P classification is actually unsupervised. It's a one-class problem. So it is not really solvable. But we found that if we have positive data equipped with confidence, we can still train a classifier. So such a only P data situation appears in the situation like this. So we are running a company and we want to know whether a certain user buys an item from our company or rival's company. So data from rival's company cannot be obtained even in an unlabeled way because of the privacy protection regulations. So in that case, we only have positive data. Or if we see scientific publications, so there's a phenomenon called publication bias. So in like physics, chemistry, medicine, so good results are published because the results are positive and they can write a paper and they can publish it. But if their experiments failed, then such papers cannot be published and they are they don't become public. So then positive samples only appear in public and negative data don't appear. So again, it's a P-only situation. So as long as we can collect positive data with confidence, it's a class posterior probability, P of y given x. So then we can train a classifier. So that's P-conf classification. Then the next and even more challenging scenario is called UU classification, unlabeled classification. So in the case of PU classification, we had positive samples and unlabeled samples. But this is even more unsupervised. And we don't have any single label, but we have two separate sets of unlabeled data. And our assumption is that two unlabeled data sets have different class priors. Like here, so we have two unlabeled data sets, and actually class priors are different. So in the left-hand side, so we have maybe 50% positives and 50% negatives. But in the right-hand side, like 80% positives and 20% negatives or something like that. So only proportions are different. Then only from two unlabeled data sets with different class priors, we can still train a classifier. We can obtain a boundary between two classes. So this is called UU classification. It's actually a natural extension of PU classification. Then, so the next one is called SDU classification. It's similar, dissimilar, unlabeled classification. So let's consider a delicate classification problem about your income or about your religion. Then it's not easy to directly ask a question. And maybe users don't really answer to the question yes or no directly. But sometimes it is easy to answer in this way. So my answer is same as that person. Like if this is me, so I say my answer is the same as this person. Or if this is me, so I say my answer is different from that person. But I don't have to reveal whether my answer is positive or negative. Just show he or she is similar to me, or he or she is different from me, dissimilar from me. Then only from such similar pairs or dissimilar pairs, so basically we can train the classifier. The research was actually started from SU classification, like similar data pairs and unlabeled data to cover the entire domain. So this is the first result. But later on, this can be naturally extended to DU classification, dissimilar, unlabeled. And also like these two are combined, and we can also train the classifier from STU data. So this is kind of pairwise information. So such a pairwise information is utilized in clustering quite frequently, but we try to use it explicitly in the classification formulation in an empirical risk minimization framework. Then finally, so we also discuss multi-class methods for weakly supervised learning. And actually labeling patterns in multi-class classification is extremely painful. Like in image recognition problems, we have thousands of classes. Then, so we have a list of thousands of classes, and finding the right label is extremely time consuming, even with crowdsourcing. And our challenge is to reduce the labeling cost, but still we want to obtain high quality classifiers. And here we consider 3 special labels, and it is called complementary label. So a standard label specifies a class that a pattern belongs to. Like this pattern belongs to class 1, or this pattern belongs to class 3, or this image contains a dog or something like that. But complementary labels are a complementary version of that, opposite one. So it specifies a class that a pattern does not belong to. Like this sample does not belong to class 1, or this image does not contain a cat or something like that. So it's a not label. Actually, giving a not label is much cheaper, because if we have 1,000 of classes, then so suppose it's not a multi-label classification, but a single label classification, then the correct one is only correct label is only 1, and other 9,999 labels are all wrong. Then basically you can just randomly choose one of the label and confirm whether this is wrong. Then it's a complementary label. If you are lucky and if it's a correct label, then it's a ordinary label, and that's quite precious. Okay, we can utilize both of them. So that's learning from complementary labels. Then partial labels are a slight extension of this complementary labels. And this has been studied for many years. So a partial label specifies a subset of classes that contains the correct one. Like this sample belongs to either class 1 or 2, or this image contains either dog or cat or something like that. So it's an or label. So it's an ambiguous label. So actually, complementary label is a special case of partial labels, and essentially we can utilize similar approaches to solve the problem. Then finally, single class confidence. So this is an extension of pconf classification to multi-class problems. So now suppose we have 3 classes, but we only have data from class 1. But suppose class 1 data is equipped with full confidence. Like this sample is in class 1 with 60%, class 2 with 30%, and class 3 with 10% or something like that. Then only from class 1 data, we can train a multi-class classifier. So that's a method of single class confidence method. So we will briefly discuss such multi-class methods later. Okay, that was a quick overview of the entire lecture. And so far, do you have any questions? If you are already satisfied, so you can actually finish listening to this lecture, because data is just to talk about the details of methods. But already I introduced all the problems that we can solve so far. So I quickly check the Slack, and okay, no questions so far. Then, so let me continue.
If you have a question, so please come to
Oh, yeah.
microphone.
Actually, I can't see anything. So in the auditorium. So.
Hi. So I
Hi.
have one question. When you talk about similarity, do you assume that this is transitive? That you make the strong assumption that the similarity relation that you see is always transitive?
So transitive in this case, what specifically do you mean by that?
Similar to B and B is similar to C, does it in your case imply that A and C are similar? Because we can have a chain of similarity is not usually transitive. You can have a chain of similar things, but eventually they get non-similar.
So when we solve a problem, basically we assume IID samples. So we consider like similar data pair distributions, and we assume we have IID samples from the similar distribution. Does it answer your question?
No. The question is, it's not, one thing is to say they have the similar label, then it's transitive, then it's an equivalence class. But if you say that two things are similar may just mean that they are likely to have the same label. In that case, I can have a chain. A and B are likely to have the same label, B and C likely to have the same label, but A and C are by now pretty unlikely, not clear if they have the same label or not.
So in our case, we only handle pairwise information. The higher order information was not directly taken into account. So maybe that was not really taken into account in the current form, but could be extended in a slightly different formulation.
Okay, thank you.
Thank you very much.
There is another one question.
Oh yeah, thank you.
Yes, one small question. Could you clarify a bit on how weakly supervised learning is different from semi-supervised learning?
Yeah, so right, that's a bit difficult question to answer. So like semi-supervised learning problem. So we use positive data, unlabeled data in addition to a small number of positive data and unlabeled data. So clearly it's a part of weakly supervised learning problems. So maybe we consider kind of variations of semi-supervised learning in a slightly different way, like only PU or PConf or different problems. And we call a set of problems weakly supervised learning. And standard semi-supervised classification is included in it.
Thank you.
Thank you. Great. So then let me continue. The first part is a boring part. I just quickly go through a standard definition and notations for PN classification, supervised classification. So for the moment, let's consider a standard supervised classification problem. So we are given label data, xi and yi in samples, and they are coming from P of x and y independently. And assume x is a d-dimensional real vector, and output is a binary label +1 and -1. So it's fairly standard. Then, so we consider classifier f that maps x to y. And label prediction is done by the sign of fx, and it is y hat. And we may use any classifier like linear model, additive model, kernel model, deep model, and etc. So I don't really specify it. It's just a function. Then for a binary problem, we specifically consider margin. So it's a product of output label y and its prediction f of x. And if margin is positive, then the sign of f of x is the same as y. So classification is correct. And if margin is negative, then so these two does not agree and classification is wrong. And to count the number of the correct answers, so 0-1 loss is often used. So it is defined in this way. So sign of m is either +1 or -1. And if the margin is positive, then so sign is 1 and 1 minus 1 is 0. So 0 for correct prediction. And if margin is negative, then it's 1 minus -1. So it's 2 divided by 2. So 1 for wrong prediction. So this basically counts the number of mistakes. Then, so based on the 0-1 loss, so we define the classification error. So this is basically the expected 0-1 loss over all test data. So we consider 0-1 loss and for x and y, and this is expected over p of x and y. It's a classification error. And our real goal is to find a minimizer of this R01. But this is impossible because P of xy, so true density, is unknown. So instead, so we assume we have IID samples, n samples from P of n xy, and we consider its empirical approximation. So the classification error is now empirically approximated in this way. Then under some standard setting, so this is actually a reasonable approximation because the estimation error is order of 1 over square root of n. If you have a large number of samples, then this empirical approximation is usually quite good. Oh, sorry. And another issue is that minimization of this empirical 0-1 risk is actually NP hard. So due to discrete nature of 0-1. So if we take the margin on the horizontal axis, then the 0-1 loss is a like negative step function like this. And it's basically a like discrete function. Then so we can't expect that. So we can find a global minimizer in practice. Then so we prefer to use a smoother version of this 0-1 loss. It's called a surrogate loss. So it's a like standard textbook things. So instead of the 0-1 loss, this red one, so a lot of different smooth loss functions were developed so far. And like hinge loss, this green one, was used for support vector machine. Ramp loss, this so light blue one. So this is used in robust support vector machines. Then this purple one, logistic loss, was used in logistic regression. Then this exponential loss, so black one. So this was used in boosting. And many existing methods can be accommodated in this simple framework. So it's quite nice. Okay, then, so instead of the classification error, we define the classification risk for the loss function L. So it is this R wave. So not L01, but L expected over P of X and Y. So this is a classification risk. And we apply empirical approximation to this classification risk. So this is the like standard training objective function. We have an empirical loss function and we minimize it. Then, so this minimization is usually done within a certain model class, like linear function class or additive function class or kernel models, deep models. So I don't really specify the model class today for the moment, but so in practice, we consider some parametric class. Okay, that was the introduction of the notations. And then let's focus on the PU classification part. So this is basically the main part of the lecture today. So let's record the setup again. So we are given positive samples and unlabeled samples. So they are IID samples from the positive data density and marginal density. So we have two sets of samples. Then from these two sets of samples, we want to obtain a classifier that separates positives and negatives. That's the goal here. So then, so we consider the classification risk, R of F. So that was defined in this way. And by standard argument, we decompose this expected risk, expected loss function into the positive part and negative part. Then here we have pi and 1 minus pi. And pi is the class prior probability, P of y equals +1. And today, actually, I assume this pi is known because then the discussion becomes quite simple. But in practice, we also need to estimate pi from data, from only PU data. And I must admit, so estimation of pi only from PU data is not straightforward. And already there's a series of research working on estimating pi only from PU data. And also I have some long slides about that. If you are interested in some details of this discussion, please take a look at this slide or some other publications. But we have some reasonable methods for estimating pi, even though still it is challenging, I must admit. So for today, so let me assume pi is known. Then, so now the risk was decomposed into the P part and N part, and suppose pi is known. Then, so we have positive data. So then approximating the positive risk is straightforward. But in this PU learning setup, we don't have negative data. then approximating this expectation over negative samples is a problem. So this is the technical issue that we want to overcome in this PU learning framework. But we have a very simple trick. So we know that unlabeled data density P of X is by definition a mixture of positive data and negative data densities in this way. And the mixing coefficients are pi and 1 minus pi. So we have P of X given Y equals plus 1, so blue 1. And we have P of X given Y equals minus 1, okay, red 1. Then the unlabeled data density is basically a mixture of these two with pi and 1 minus pi coefficients. So that's the definition. And we utilize this. So by moving this px on the right-hand side, no, this one to the left-hand side, then we have this relation. So density of negative samples is given by P of X minus pi times P of X given Y equals plus 1. And we use this relation to eliminate this expectation over negative samples. Then, so this term is basically decomposed into two terms in this way. Then the classification risk is now consisting of 3 terms like this. But expectations are only over positive samples, unlabeled samples, and positive samples. So then we can naively apply empirical approximation to obtain an empirical risk from this expression. So that's the issue here. So by replacing the expectations by sample averages, we can obtain an empirical risk for PU classification in this way. So we have positive samples twice, but they are just some, so it's no problem. And we can show that it is unbiased, and following some standard theoretical analysis, we can show that the convergence rate is actually optimal in parametric cases, like this. So it's order of 1 over square root of NP and 1 over square root of NU. So NP and NU are number of positive samples and unlabeled samples. It's a standard analysis, like standard supervised learning. Then, okay, the problem was almost solved. And here's one comparison with standard supervised learning, PN learning. So we can actually obtain a similar estimation error bound for PN learning, supervised learning. Then we really have very similar expressions like this. And we have common constant C delta. Then actually we can compare these two coefficients here. Then actually we can show that upper bound of this PU classification is smaller than the upper bound of this PN classification if this condition is satisfied. I just compared these two terms and show the condition. So this roughly means if you have a large number of positive samples, then left-hand side tends to be small and PU learning tends to be better. And if you have a large number of unlabeled samples, then so this term gets small and left-hand side tends to be small. So PU learning tends to be better. And if you have only a small number of negative samples, then PN learning gets worse and right-hand side gets larger. Then PU learning tends to be better. So by looking at this condition, so we can compare whether PU learning is good or PN learning is good. So if you have a large number of positive data and unlabeled data, and suppose we have only a small number of negative data, then so we recommend to use PU learning because of this bound. So relying on a small number of negative samples is actually not a good idea, but instead we can utilize a large number of unlabeled samples. And later on, today actually I omitted the slide, but we can also combine PN learning and PU learning. Then actually we can even improve the performance, but this is not covered today. Okay, then so that was the first story. So we can obtain an empirical risk approximation easily by some small manipulation. But we have a still a bit problem. So what we have done so far was we used basically this relation. So unlabeled data density is a mixture of positive data density and negative data density. And this risk for negative data, R minus, was re-expressed in terms of only unlabeled data and positive data. And this is what we have done so far. And here, suppose the loss function is non-negative. Maybe this is the standard condition. As long as it is lower bounded, we can always satisfy this condition by shifting it. So then, so R minus is just the expectation of this L function. So R minus is also non-negative by definition. But now we apply so empirical approximation based on PU data for this R minus. Then we use actually this expression. So difference of two terms. Then actually this empirical approximation R hat can be negative due to the difference of approximations. Because suppose R minus is positive, like x3. Then the first term is 5 and second term is 2. Then 5 minus 2 is really 3. But now we don't know 5, 2 either. We just approximate them from samples. Then 5 is estimated to by 3, for example, and 2 is estimated by 4 or something. Then, so now it's 3 minus 4, and it becomes minus 1. So then, this means even if the loss function is non-negative, okay, this empirical approximation of R hat minus can be negative. And this problem happens actually for complex model. In particular, if you use neural networks, then so this negativity problem almost always appear. It actually causes a heavy overfitting in practice. So here's a simple numerical illustration. So I took the stochastic gradient iteration on the horizontal axis. Then for standard PN learning, so suppose we have positive samples and negative samples, then so this blue dotted line, so it's a training error, empirical error. So it decreases monotonically like this. Then the test error, so this blue solid line, this also decreases nicely in this way. So this is the standard situation. But in PU classification, so we have so this red dotted line for training. Then at some point, it really becomes negative, and it really goes large negative value in this way. So empirical error goes negative. Then interestingly, the test error actually started to grow at around this point, and it started to overfit, and test error increases. So this is the problem of specifically to weakly supervised learning. So we decided to constrain the sample approximation term to be non-negative. So in this way, so this is basically R hat minus. So we take max 0 here. So once this term becomes negative, then we round it up to 0. So then we can in principle prevent the negativity problem. But then we lose unbiasedness. So the risk estimator is biased. So we should ask whether this non-negative correction is really a good thing to do. And we had some theoretical analysis for that. So now R tilde is the one empirical approximation with the non-negativity correction like this. So this R tilde is still consistent, and its bias decreases exponentially fast. So we have this order. So this means that it is slightly biased, but bias can be in practice ignored. So it's no problem. Then, so the second thing is the mean squared error of this R tilde is not more than the original one. So this means in practice, R tilde is more reliable than the original negative ones, potentially negative ones. Then finally, so the risk of the minimizer of R tilde for linear model class attains the optimal convergence rate of this order. So this means that this is still slightly biased, but the obtained solution is fine. So it is still good enough. So these are the theoretical justifications to use this max 0 correction. Then later on, we even found that similar kinds of theoretical results holds also for, so this is actually a ReLU function, right? So if it's negative, it is 0. And if it's positive, it outputs the same value. It's a ReLU correction. And we can actually extend the same kind of result to leaky ReLU function. And it's generalized leaky ReLU function. So we actually have negative slope on the left-hand side. So usually leaky ReLU has negative, positive slope here on the left-hand side, but we have negative slope on the left-hand side. But still, we can guarantee the similar thing. And actually, this is quite interesting algorithm in practice, because so suppose this part is non-negative, then so we can ignore this correction part because we just have the same value. Then we have the standard gradient descent for mini batch of samples. But suppose this part is negative, then so we have this purple line, so the generalized leaky wave function. Then actually the gradient is negated. So this means that so we actually perform gradient ascent for this mini batch of samples. So this is a bit counterintuitive in practice, but so we can intuitively understand this phenomenon in this way. So we know that if this term becomes negative, then our solution often overfits. So in a sense, so being negative or positive, so this is a kind of precaution of overfitting. Then if we find that, so okay, this part becomes negative, and this implies that so after a few iterations, our solution will be trapped by some local optimum, and our solution is overfitted. Then it's a nice precaution. So then we should be away from that dangerous local minimum. So by performing gradient ascent, we can actually step back from this local optimum. Then in the next iteration, we take another mini batch of samples and compute another gradient and go to different direction. So by performing this gradient ascent, we can somehow effectively escape from poor local optimum. So there's no theoretical analysis for that, but intuitively this leaky wave correction works in that way. And the performance is often improved in practice. And also we can extend this like leaky wave correction idea to many different problems, not only in weakly supervised learning, but noisy level problems and some others at the same time. Okay, so let me briefly talk about one nice application we had last year. It's about signal enhancement. So we presented it at ICASP last year, and this was actually a best paper award. But it's a natural application of PU classification to signal enhancement or signal denoising. The goal is quite simple. So we have noisy signal, and we put it in some signal enhancer or noise remover and obtain clean signal. So that's the goal. And in the standard existing methods, they use noiseless parallel training data. So to learn this signal enhancement part, they needed so noisy signal and clean signal for the same input. So these are called parallel training data in the signal processing communities. But of course, in practice, it is not possible to obtain like noiseless and noisy data at the same time in parallel. Then in practice, so they use synthetic data. So they prepare some clean signal and add synthetic noise and have clean version and noisy version and train an enhancer. So that was the practice that they've done. But if we apply PU classification, then so we don't need parallel training data, but we just need two sets of samples, positives and negatives, positives and unlabeled. And here, actually, positive samples are noise-only samples. So below here, so we collect noise in some environment. So these are regarded as positive samples. Then also we collect like speech in noisy environment. So this is a mixture of noise and speech, and it's unlabeled actually. Then only from noisy signals and pure noise signal, we can train a classifier to separate noise and speech. And we can perform like signal enhancement or denoising. And compared with some existing methods, our method actually works much better than such non-parallel method. And compared with the parallel data method, this is supervised, and it is actually closer to the performance. So this means that this PU classification-based approach is quite promising, even though it's a simple application of PU classification to signal enhancement. Okay, so that was the summary of PU classification so far. And do you have any questions?
Yeah, of course, I have questions.
Yes.
So, yeah, I have a few questions about this PU framework. I mean, the first question, I guess you said you answered in some slides. I mean, without having any negative data, how can you estimate pi? To estimate pi, you need some negative data. That's my first question. The second question is that in order to get this 1 over square root of n rate, you need to assume that we do ERM over a limited class of functions, say a class of finite VC dimension. Otherwise, we cannot get. But if it's a limited class of functions, then we also have a bias of the class. So we don't get a result that gives me an upper bound on the error, but only upper bound on the excess error compared to the class.
So what do you mean the bias of the class?
I mean, the best in the class is not 0 error. It's not realizable. The best predictor in the class doesn't make 0 error.
Right.
Because we need to assume that the class is finite VC dimension. Otherwise, you don't have the square root of 1 over n.
Yeah. For the second question, so right, we consider like limited function class, and we try to find the best approximation in that class. So
right.
that's something we can do the best.
Right. So the error that you get is excess error compared to the best in the class.
Right.
My last question is about this. There is another factor that intuitively should come into it, and this is the probability that I'll see a label given a point. I mean, if the point is negative, the probability I'll see a label is 0. If the point is positive, still the probability that I'll see the label can vary between points, and that can affect the data collection. It's not a constant. Even when it's positive, it's not a constant probability that I'll see that it's positive.
So I don't really, I'm not sure whether I really took it correctly, but so we have like 2 different formulations. One is like our kind of formulation. We have 2 sets of like training data, positives and unlabeled. Then another one is only like 1 sample setting, but they have another like latent variable that shows whether we observe a label or not. And in the case of negative label, we don't observe it. But in the case of positive label, we observe it or something like that.
Right. So you assume that in the case of positive label, you will always observe the positive label. Because in reality, there could be a good advertisement, but the user didn't click. So there is a probability that you will see that it's positive, given it's positive. There is another factor here. How was the data collected? What is the assumption on how were the positively generated?
Yeah. So first of all, okay, we are aware that we have like 1 sample setting and 2 sample setting, and 2 sample setting is actually more general. It contains 1 sample case as a special situation. So that's why we focus on the 2 sample case. And for the data generation mechanism, maybe I can't really figure out so how I should explain that. But
okay, so
yeah, but it is included in principle, so it should be handled also in this framework.
Okay, thank you.
Then so okay, this pi part. So this is right. So the most challenging part, and I tried to include slides for this today, but then the lecture became so long, so I in the end gave up. But okay, right. So estimation of pi is actually not always possible, and we need some assumptions if we really want to estimate pi exactly. So the simplest situation is that so positive class and negative classes are separated in some region. Then we can obtain like pure positive samples in some region. Then sometimes they're called anchor points or irreducible condition or something like that. Then under such assumption, we can really estimate pi. But without that assumption, so I think all algorithms gives an like overestimated solution to pi. So our pi hat is always larger than 2 pi. Then actually the last paper, so here, so I clear 2022, we had a nice correction method that reduces the bias in some way. It's called regrouping technique, but still bias remains. So you are right. This is a kind of really difficult and impossible problem, but we started to have a reasonable solution, and we have a kind of rough knowledge of pi from such a method. And in the worst case, in practice, pi can be regarded as a tuning parameter. And if we have some additional like validation data, we may choose pi. And at least for that purpose, so these like previous methods can be used to like know the range of pi reasonably. Thank you very much. So then the PU learning part was done. So pconf part is quite short. I just quickly go through it. So now pconf classification. So data is a pair of X and R. X is an IID positive samples, and R is its confidence, P of Y given plus, Y equals plus 1 given Xi. And data is something like this. And we want to learn the boundary like this. Then, so the same kind of recipe. So we start from the classification risk, and we want to estimate it only from P-conf data. And naively, like if one point is like 80% positive, then that point is 20% negative. So we may split like this loss into R, L, and 1 minus R, L minus. So that's a naive confidence weighting. But in this case, this is not really true because the expectation is taken only over positive data. If you have unlabeled data in that way, then so this is possible. So in the current case, we also need to have importance weighting to change the distribution from this to this. Then in the end, the correct form is rather similar but a bit different. So we have pi here and no weight here, and we have weight 1 minus R divided by R. So by a few lines of calculation, we can obtain this. And in the end, this results in an empirical risk of this form. And good news here is that pi is only a proportional constant. So for training, we can drop it. So we don't have to estimate pi in this P-conf formulation. We only need Xi and Ri. Okay, for P-conf, just like that. Then let me go on to the next part, UU classification. So this is quite interesting and challenging. So now we have two sets of samples, unlabeled samples. One is coming from P of X, and the other is coming from P prime of X. And we assume that Py and P prime Y are different class pairs, but we assume that so class conditional densities, P of X given Y and P prime of X given Y, so they are the same. Like consider mixture of Gaussian setting, and we only assume that Gaussians are the same, but the proportions are different. Like in this way, 50-50 and 80-20 or something like that. Then we want to still train a classifier. And one of the oldest method for this problem was studied already more than 10 years ago. And in this paper, we consider the sign of the difference of class posteriors. So by computing this quantity, we can perform correct classification. Then if we assume, so okay, I said we have class priors are different, and we need to consider one more prior for test data, because from this formulation, so it's not clear where the test points are coming from. So we assume that test priors are uniform, 50-50 in this paper. Then, so this optimal classifier G is expressed in this simple form. So C is a constant that cannot be estimated from any label. But the second term, the second term, sign of Px minus P prime X. So this can be estimated only from unlabeled samples. So then by naively performing density estimation from two sets of samples, or in this paper, actually, we try to directly estimate Px minus P prime X. So density difference was directly estimated. Then actually we can obtain the boundary. But still, like we can't identify the direction of the boundary because we only obtain the line here, but we don't know which side is positive and which side is negative because C is completely unknown. But in practice, maybe we need one labeled sample to know the direction of the boundary, but maybe this is not a big issue. So that's the basic method. Then, so we try to kind of interpret that idea in the empirical risk framework. Now we assume that the test prior is uniform again, so pi is 1/2. Then suppose we use a symmetric loss function. So this is satisfied. Then it's a robust loss function actually. Then the classification risk, so defined in the same way, this can be expressed in a very simple form like this. So we omitted some proportional constant, and it's just the empirical risk. So one set is regarded as positive samples, and the other set is regarded as negative samples, and we have some constant. Then we can drop all the constant, and in practice, so training can be done based on this criteria. So just one set is regarded as positive samples, and the other set is regarded as negative samples, and minimize them. Then, so we can actually obtain a solution. And so this was the result for like this pi is 1/2, and we have symmetric loss function. But this can be generalized, even if the test prior is not uniform. As long as we know the test class prior and also priors for P and P prime, then we can still obtain the solution. But for the uniform test prior case, so it's a kind of magical and all constants disappear and we can obtain the solution. It's a special case, but it is an interesting solution. Then, so this method can be naturally extended to UUU classification. So now we have M sets, MU sets, and UM classification. Then one potential solution is to apply this UU method for pairs of U set. If you have 10 unlabeled data set, then we pick 2 of them and form UU classification and combine them in the right way. But the combination grows exponentially when M is large, so it is computationally quite expensive. Then we had a simple solution called surrogate set classification. So now we have an M-class classifier, Fx, that probabilistically assigns the dataset ID to each sample. So we basically regard it as a multi-class problem. We want to identify the dataset ID from a sample. Then based on this classifier, so we can actually determine the class posterior probability deterministically from this f of x. So that's a solution. So I don't write the exact definition of T here, but it's like a deterministic quantity. So by that, we can handle more than 2 unlabeled data sets properly. Then that was about pconf and UU classification. And any questions? I had one question in Slack. So in weekly supervised learning, latent variables could often implicitly influence the labeling process. Is there some approach to take this into consideration for the labeling? That's a very good question. So in our simple framework, we just assume that our weekly supervised data IID from some distribution. So we didn't say more than that. But maybe as an example of latent variable, so the one sample setting, like in the PU case, we only have one sample, but depending on the latent variable we sample, so sometimes the label is observed and sometimes not. Maybe in that kind of process, already it is included as a special case. But if you consider more elaborate data generating process, a label generating process, maybe we need some more specific technique to handle that. So this is not really covered in the lecture today, but hope that you can have some concrete example, and it's nice to consider a solution for that kind of problem. So thank you
There is
very much.
one question from the audience.
Yes, thank you very much.
Yeah, I have 2 questions. Why do you consider it's rather a simple one? Why you consider pconf dataset harder than labeled dataset? Because it's kind of seems more richer. For each point, I kind of not having a label, but kind of class distribution. It feels that this dataset is actually more richer dataset than just labeled ones.
Yeah, thank you very much for the very nice question. So maybe, right, so it's a matter of expression. So like from the, I try to compare this approach with PU classification. Then in the PU case, we needed P and U, two data sets. But now U is not available, but still we want to perform classification. So that was the starting point. So P only classification, but this was impossible. Then we assume that, okay, we have some additional knowledge, right? So from that viewpoint, this additional confidence score is like stronger supervision. So, right, so maybe we can simply say like this is like weaker than like PN classification. So, right, so it's just a matter of expression, but we are solving this pconf problem directly. And from the like available data set, so P and U, so we only need P data.
Okay, thank you. And can you go to the slide 38?
Yes.
I kind of have a questions about convergence property for this PRUU, because kind of it will be good only if PX distribution over X and distribution prime over X's and joint models could be quite different, because imagine if you have 2 kind of identical distribution over first data set and the next data set, then this optimization does not make any sense. Can you kind of elaborate about how convergence properties depends on the distances between p probability of x and probability prime x distributions?
Thanks for the great question. So basically, our assumption relies on this one. So py is different from p prime y. And right, if we do theoretical convergence analysis, then the difference between these two appear explicitly. So suppose in the extreme case, so we have like 100% positive on the left-hand side and 100% negative on the right-hand side. Then this is purely a supervised learning problem. And this is included as a special case. So that's the easiest situation. But if these two are like quite close, like 50, 50, 50, 50, 45, 50, 49, 51, and 51, 49, or something like that, then so two data sets are almost identical. Then the problems are, you are right, very complicated and quite challenging. So this is almost impossible to solve. Maybe we need some additional knowledge to separate the two classes.
Yeah, but my question was kind of about, do you have some bounds how far they should be that problem will be solvable? Maybe
theoretically, as long as they are epsilon different, it is possible to solve if n and n prime are large enough.
Different epsilon different in what divergence, what metric? What do you mean?
It's just a scalar, right? So 49% and 50% or something.
Okay, thank you.
So it's relative to the number of samples.
Okay.
Okay, thank you very much. So then the next part is STU classification. So this part is also rather simple. So now we have like similar and unlabeled samples. So this was a question from Shai in the beginning. So we consider like this joint distribution, and we have IID. We assume we have IID samples from that, and also we have set of unlabeled data. Then from that we want to obtain a classifier. Then given this formulation, actually we can decompose this pair into like a set of two NS samples. Then actually we can apply a UU classification technique to this problem. Then in particular, so for the first set, so we have this class prior. Then for the second set, we have like pi, original pi. So these two are different. Then so we can solve the problem. So there's no new method in principle to solve this problem. Then the same thing also happened to DU classification and ST classification. So we have like we can set P and P prime in this way. Then we can solve the problem with the UU classification method. It's a fairly general classification method. And by combining so DU, SU, ST, by actually linearly combining the criteria, we can also solve STU classification. So that's the trick here. Then okay, we have a lot of extensions for this ST classification problem. The first one is noisy ST problem. And we can actually consider two types of noise. So first one is called pairing corruption noise. So expressed in this way. So we have X and X prime and Y prime. Then from that, so we consider pairwise similarity or dissimilarity, then add noise. So that's one noise model. Then another one is labeling corruption noise. So we have X and then noise, label Y, then we have noise. So Y underbar. Then so X prime also has label Y prime, and we have noise. So Y prime underbar. Then we compute the similar dissimilar label in this way. So we consider these two corruption models and we gave solutions to these problems. Then variations are also here. So one is called similar confidence classification. So we assume that we have IID samples from like this data for positive samples. But now, so we have similar pairs with confidence. So it's similar to pconf, but so we have similar pairs and confidence. Then we can solve the problem without having unlabeled data. Or pairwise confidence comparison is also possible. So sample pairs with one having larger positive confidence than the other. So we don't have to know the positive confidence value, but given a pair of samples, so we just say one has higher class posterior than the other. Then from that comparison information, we can still train the classifier. And finally, the confidence difference. So sometimes exactly observing the confidence is not that easy, but sometimes it is possible to observe the difference of confidence. Then only from the difference of confidence, without knowing each confidence separately, we can still train a classifier. So these are variations, and they have some nice applications in their own domains. Okay, that was about STU classification. So then let's come to the complementary classification part, multi-class problem. So as I said, labeling patterns in multi-class problem is quite painful. So selecting a correct class, correct class from a long list of candidate classes is extremely painful. Then we construct complementary labels. So that's the formulation here. So then, our initial formulation was given like this. So we assume that, so we have some P bar behind. So it is actually defined in this way, the average over Y. Then, so from this P bar, so we have IID samples. It's a pattern and complementary label. Then, so pattern X does not belong to class Y bar. And from this X and Y bar, we want to obtain a multi-class classifier. So that's the formulation here. So then, so to solve the problem, so we consider the C-class classifier, so f of x, so it's given by gy. So gy is the one versus rest classifier for class y, it's standard. Then, so we use the C-class loss function, capital L. And then, so typical examples are one versus rest formulation, and also pairwise comparison like this. So these two have been studied for many years, and standard multi-class classification loss function. Then the C-class classification risk is defined in this way. So we have multi-class loss expected over the true density. So this is the risk. And we follow the basically same recipe, and we want to estimate this RG only from available weak label data. Then here's a method to estimate the risk only from complementary labels. So original definition was like this. Then, so after a few lines of calculation, we can show that this risk can be equivalently expressed as in this way. So P is replaced with P bar, and Y is replaced with Y bar, and L is replaced with L bar, like this. Then, so we can naively apply empirical approximation to this one. And this L bar, definition of this L bar is quite tactical. And so it's called complementary loss. And L bar is defined in this way. So we have original L here and here, and we have Y bar here, and also like all labels here, Y. So by this formulation, we can have, again, consistent solution by minimizing this one. Then also, so this complementary classification methods have been generalized in different directions. The first research was about from unbiased risk estimation to surrogate complementary loss function. So the path we took so far was, so we started from 0,1 risk functional. Then this was approximated by the surrogate loss, RL. Then this was estimated with weekly supervised data. And finally, we applied empirical risk approximation. This was the original path. But in this paper, we considered another path. So we first tried to express R01 with complementary labels. Then so we approximated it with a surrogate complementary loss phi. Then finally, we applied the empirical approximation. Then by that, we can find that actually gradient estimation for training a neural network is more stable in the latter approach. Then the second generalization is about multiple complementary label. So in multi-class problem, in principle, for the same sample, we can consider many different complementary labels, because wrong labels there are many wrong classes. And basically, this is essentially the same as partial label formulation. And we have some, so Y bar, so that contains multiple complementary labels. And we consider a different set size. So S is from 1 to K minus 1. So this is the number of complementary label. And we consider the data generation, label generation formulation in this way. Then essentially the similar kind of technique can be applied to solve multiple complementary label problem. Then finally, so release from the uniform assumption. So in the original paper, so the data generation, label generation was considered in this uniform way. But this could be a very strong assumption. And there is actually another extension that can consider like non-uniform distribution. But then so-called label transition function, transition matrix has to be known or has to be estimated. And this is again another big problem. But by considering the actually one sample setting for this problem, and we choose, we select label completely at random, then actually we don't really need a strong uniform assumption, but still we can solve the problem. So this is still a new work, but we have a fairly general formulation for complementary label learning in the end. Okay, so that was the end of the technical part. And do you have any questions for the STU part and complementary classification part?
Seems no question.
Okay, so great. So then let's come to the final part and you can have a bit longer coffee break. So in this talk, we talked about empirical risk minimization framework for weakly supervised learning. And because, so our recipe was quite straightforward. So we first defined the risk function based on a loss function. Then we tried to express the risk functional in terms of the available weak supervision. Then we applied empirical risk approximation. So it's quite simple. And then, so because of this simple formulation, any loss function can be used in principle, and any classifier can be used in principle. And you can add whatever regularizers you want. And you can also use whatever optimizer to obtain a solution. So thanks to this simple formulation, we can utilize many different machine learning techniques to enhance the methodology. And also, so to explain each problem, I discussed the PU, PConf, and STU separately, but all are empirical risk minimization based. So this means that we can actually easily combine them. So suppose you have positive data, negative data, unlabeled data, similar, dissimilar, PConf, NConf, SConf, TConf, whatever. Then all of them can actually join to estimate the empirical risk and improve the solution. So this is a kind of advantage of this framework because everything is about simple empirical risk minimization. So methods are seemingly independent, but they can be often combined. So that's an advantage of this formulation. Then, so the last issue. So we are working on this weakly supervised learning methods as a part of so reliable machine learning research. So we want to improve the reliability of machine learning. So if we have weak supervision, still we want to have a reliable machine learning solution. So that was the target so far. And our basic approach was the reliability for kind of expectable situations. So we model the corruption process. In the case of weak supervision, we assume we know how the weak labels are produced. Then based on that corruption process or generation process, we corrected the solution. But sometimes, depending on the problem, so we don't really know the corruption process or data generation process exactly. Then we may have some modeling error. So how to handle this modeling error is still an open issue. Maybe it depends on the problem, but we need to also explore this. Then another completely different approach would be to consider reliability for unexpected situations. So like suppose, so we don't know anything about the test phase, then we may consider the worst case robustness or minimax solution. So something worst happens in the test phase, then we try to minimize the worst case risk. So this is a standard solution, and we may obtain a nice solution mathematically. But in practice, so we need to consider certain epsilon ball or something to consider the robustness, worst case. Then, and the solution tends to be very conservative. So our worst case scenario is really the worst case, and maybe it doesn't happen in practice, but still we need to cope with it. So if we take this minimax approach, how to make it less conservative is an ultimate challenge. Or sometimes we prefer to include human support, like rejection, for example, or human feedback. So then, so if something wrong is happening, we can stop it and we do manual processing. But this is possible only for like offline applications, like medical image processing, medical image analysis. This is possible. But if it's an autonomous driving car, the car is already running and maybe human drivers is not driving a car anymore, then we can't really include human support for recognition. So how to handle real-time situations is an open issue for this human support direction. But in practice, maybe considering somewhere in between these two, perhaps we have some partial knowledge of the corruption process. Maybe some are correct and some are not. And we want to utilize that. So exploring somewhere in the middle would be practically more useful. And we want to utilize partial knowledge of the corruption process. So this is still an open direction, but hope that we can combine like this weekly supervised learning research and label noise research. And also, so in the next class, I think transfer learning will be discussed. Transfer learning is another like data bias issue. And these three are actually quite related to each other in the formulation level. And hope that we can combine all of them and have a kind of unified solution that can be applied to like quite a broad situation. Because nowadays the difficulty of applying like sophisticated machine learning techniques is that we need to know the problem quite well. So like we have, so if we have some additional knowledge or assumption, then we can have a stronger method. But to apply a stronger method in a reliable way, we need to kind of assess the assumptions made behind. But often this is very difficult. So that's always a big problem. So in reality, we want to have a single method that is fairly general, maybe not so powerful, but quite general and has some minimum support, theoretical support. Then, so we can use that kind of method in the beginning and see whether machine learning is really useful in that context. And if we find that machine learning approach is useful in that application, then, okay, spend more funding to collect more data or study more about the problems behind. So then we have more knowledge about the problem and use that knowledge to apply more sophisticated machine learning technique. And to do so, we need the first method, very general machine learning technique. And I think following this line of research could be contributing to generating a fairly general machine learning technique. That's something we are tackling now and hope that so we can have some nice method in the future. So then this is essentially the last slide I prepared. And I had one more question in the Slack. So the IID assumption is often needed in today's content. Is it possible to solve the weakly supervised problem when facing out of distribution data? Yeah, so this is always a question to handle out of distribution data. And it depends on like how we define out of distribution data. Like a naive way is to apply some like outlier. If it's a training data, so we apply some outlier detection method to get rid of those out of distribution data. But if it's a test data, then we need to have a kind of transfer learning problem, right? Maybe in the next class, you will hear more about transfer learning. But then, so it's a kind of combination of weakly supervised learning and transfer learning problem. And I believe this is possible as long as we have some knowledge of the out of distribution data. If there's no knowledge about that, then we may have to consider this kind of worst case robustness or some human support or some other approaches. So this may be still open, and I don't know whether we have a guaranteed method for these approaches, but there must be some room for improvement at this moment. And one more question here. So please explain more on including human support. So rejection. Oh, okay. So the simplest case, so okay, let's consider binary classification problem, and we have class posterior probability, the confidence. If confidence is larger than like 70%, okay, we classify samples automatically. But if the confidence is less than 70%, then it might be wrong or ambiguous, then let's ask human expert to judge it. And this kind of human support is quite important in medical application, for example. So if you want to identify whether like this cancer is really malicious or not, then if the AI prediction is ambiguous, then it's natural to ask human expert, medical doctor, to really investigate it. Maybe they have to do more careful investigation by doing more experiments. Okay, then let me read one more question in Slack. So in very applied approach, in the PU framework, I fit the logistic regression on P and non-P and predict on my sample. After that, I assign P to the observations for which the predicted probability is higher than a certain threshold. If I fit one more time, okay, right. So it's repetition. So how do you perform this in the first iteration? Maybe that's the question. Suppose you have P and U, and naively you may regard all unlabeled data as negative and do classification. Then have the first classifier, then apply this classifier to label unlabeled data and extract P data and N data, then train the method by PN method. So maybe this is possible, but then clearly the first round is problematic, right? So yeah, so I'm aware there are several approaches. It really does this kind of iterative approach, but then so estimation of pi is actually included. Class prior probability is included in that iteration. Then so if things are going well, maybe that's a good approach. But if the initial guess is not really correct, then I don't know where does the iteration goes. So there's no strong guarantee for that. So I think the approach is quite interesting and useful in practice, but still more theoretical discussion would be needed for this kind of iterative approach. So one more question. So
Yeah,
are there works in which PU, NU, UU, etc. are considered in active learning scenario where the learner can query true labels? That's an interesting question. I personally not quite familiar with that, but mathematically this is a possible problem formulation. And if you can find a nice application of these like active learning scenarios for weekly supervised learning settings, then that method should be quite useful.
Please go ahead.
Question? Yeah.
Yeah, so my question was like regarding these frameworks which extend ERM to weekly supervised scenario. What is the sensitivity of these methods to the fixed label data that we receive, or the quality of the fixed label data that we receive? Because if you receive few amount of label data, then I suspect that these frameworks would be very susceptible.
But what do you mean by fixed labels?
Fixed amount of labels for the positive or negative classes, like in semi-supervised or weekly supervised setting that
you mean
explained.
small number of samples, essentially?
Yeah, small number of samples, or even like, the stability of the algorithm in terms of when I change the data set or I sample different positive samples from the distribution. So do you have any comments on the stability of these frameworks that extend ERM?
Yeah, thank you very much for the very nice question. So like for small sample performance, so maybe we can't really say anything. So it's similar to standard supervised learning, but even weaker. So maybe our method will suffer more from small samples. Then in terms of stability, also there's no clear analysis for that, but yeah, at least so same as standard supervised learning, such weekly supervised learning method also suffer the same issue, or maybe even more severely because of weak supervision. But I'm not really aware of the exact analysis for that.
Thanks for the answer.
So I have one question. So
Yes.
I believe the weekly supervised learning also helpful for privacy preserving or fairness in machine learning. So could you comment on that?
Yeah, thank you very much. So for privacy preservation, so maybe this could be opposite, right? Like from weekly supervised data, so like we expect that we don't really provide strong information, but still we can train the classifier. So this is good and bad. Like in SU classification, for example, I don't want to talk about my labels explicitly, but just by providing similar dissimilar information, then basically my information can be revealed, right? So this is a bit danger of weakly supervised learning because it works well. So it can be used for revealing privacy information, even though users are not aware of that. That's one thing we should be careful about this. But of course, we should utilize this kind of weakly supervised learning technique in a more positive way. So even with limited like supervised information, still we can really build a useful machine learning technique. But maybe we need some additional mechanism to protect privacy information, even in this weakly supervised learning framework. That is still missing, I think.
Thank you. So any other questions or comments? Okay, so yeah, let's conclude this session. Yeah, thanks to Masashi again.
Exactly on time. Thank you very much. Have a nice day.